and welcome. I'll be going through the simple harmonic motion questions that were in the specimen papers for the new spec. So this is a 7408 spec. So we'll be going through these questions here. There are simple harmonic motion questions, and they're a mix of, there's only a couple here. So there's a big long question here, and I've got 3 multiple choice that came up in the 2 specimen papers that were given out. So let's begin. So this question here, state the conditions for simple harmonic motion. This question comes up so much. They sometimes say define what is meant by simple harmonic motion and things like that. So state the conditions for simple harmonic motion is that, of course, acceleration is proportional to displacement, and that this is in the opposite or negative direction. So in other words, A is proportional to minus X there. And that's worth 2 marks. We're just going to grab the mark scheme here. So SHM is when acceleration is proportional to the displacement, and the acceleration is the opposite direction to the displacement there. So you get 2 marks. You get 1 for saying this here and 1 for this here. Okay. So the next question, a rigid. That's a standard question. This is when you get a situation. So a rigid flat plate is made to vibrate vertically, so it's something that's bouncing up and down with simple harmonic motion. The frequency of the vibration is controlled by a SIGGEN, found in figure 1. So I've got a lovely plate here, and I've got a vibrator, and that's being forced. What I'm forcing the oscillation, and I'm making this thing oscillate. The velocity time graph for the plate for one frequency is shown in figure 2 here. Show that the maximum displacement of the plate is 3.5 times 10 to the minus 4 meters. So this one, what I'm going to be doing here, so this is a one here that I know that Vmax, I'm going to be using the fact that the graph here. Now this kind of thing comes up a lot in set paper 2 as well with EMF is BAN omega sine omega t. Okay, so the relationship of this graph is actually V equals minus omega sine omega t. I apologise, it's minus omega A sine omega t. And that's not on your data sheet at all. But that there is something that's, this equation is what this graph represents, is V equals minus omega A sine omega t. So the maximum V, so it's maximum displacement here. So the maximum displacement here is actually the amplitude. And what I'm going to do now, I'm going to use an equation that's actually on your data sheet. That is Vmax equals omega A. And of course, A is the amplitude, and amplitude is the maximum displacement. So first of all, I need to find this omega. So omega equals 2 pi f here, or of course, it equals omega equals 2 pi over t. So I'm going to use this to help me find what this is. So if I actually look for the time period, I know that t is going to be from this position here to this. So that's 50 milliseconds. So omega is 2 pi over t. Grab a calculator. So 2 pi divided by 50 times 10 to the minus 3. So that's going to be 125.7. And my maximum V, of course, is 0.044. So I can use this formula to find this amplitude. So 0.044 equals 125.7 A. So my amplitude, of course, is that 0.044 divided by the answer, and I get 3.5 times 10 to the minus 4 meters. So this question itself is worth 2 marks. One for working out what omega was, So I did 125.7. Some people work out the frequency and use 2 pi f. It didn't matter. But you got 1 mark for working out this section and 1 mark for doing this. But what it hinges on is that when you have a graph that is a sinusoidal graph like this, that using the maximum points is really, really useful because, so this is a sinusoidal graph, this is the actual equation. This is actually, if you had an EMF graph, it would be EMF equals BAN omega sine omega t. When it's maximum, this sine omega t bit actually equals 1, so it disappears from the equation. And you can actually work out these two sections here. So in the case of EMF, it would be BAN. But in this case, BAN omega, sorry. And in case of SHM, you're working out omega times the amplitude. So it's a neat little trick to realise if you're given a sinusoidal graph and you're asked to actually work things from it that aren't the frequency of the time period, that you can actually use them to find maximum things. So make sure to have a look at that one there. So next question. So I'm going to zoom out a little bit on this one because it's a big graph. It says here, draw on figure 3 the displacement time graph between 0.75 and 75 milliseconds. So I've got a graph here of velocity thing. So this graph here, they love doing this, it is supposed to be the integral. So this integrated, and you don't need to know about integration, but whatever this is, the gradient, this represents the gradient of that graph. So what I like doing is looking at certain points. So what I'm going to actually do, I'm going to actually copy and paste this down so we can actually see both side to side for a bit. Cool. So just going to make it a bit smaller so we can see it. Ooh, there we go. So what I have here is I know that the amplitude of my oscillation is 3.5 times 10 to the minus 4, which of course is 0.35 millimeters. And the reason I'm using that is because if you look at this side, it's 0.35. So at the start, I have 0 velocity. Okay, so if you remember oscillation, that when I have maximum displacement, I have maximum acceleration and I have 0 velocity. When I'm back at the equilibrium point is when I have my maximum velocity here. So we start at 0 velocity, so it's not moving. So I must be here. I must be the furthest away. And of course, if I was to draw a gradient at this point, because it's going to be a sinusoidal graph, it will be 0 at this point. This point here, I'm at maximum negative. So this must mean that I'm at the equilibrium point. This is in between 0 and 25. So this is here. Okay. At 25 millimeters, I have got a velocity, but it's in the positive direction. So if you think about it, when I push out here, when I'm at the equilibrium point, the velocity, the motion of the velocity is going to be moving this way here. Okay, so we're going to have here is a nice, there you go. So it goes down here. And then of course I have 0 gradient there. So again, this is a maximum negative gradient. I'm at 0 again, so up here. At this point here, if you go back up to the graph, I have so 25, I've got a maximum negative. So, sorry, it's really hard to draw when you're like drawing all of this kind of thing here. I don't want to draw a cos graph, but it's just making sure I'm explaining it correctly to you guys. So at this point here, I have 0 gradient. So I'm at a peak. This point here, I have maximum sort of a negative, and if you draw a line here, I've got a maximum negative gradient. At 25, again, I've got 0 velocity, so I must have a maximum here. So this is 0 gradient here. This position here, I've got a positive, so I've got a nice positive gradient here. At 50, I'm back at 0. I'm back at I'm at sort of 0 velocity, so I must have a point where I'm at 0 gradient, so we're back at a peak. And then we go back down here, and then we end up all the way back down here. Oh, that was horrible. So I'm going to try and draw this, bearing in mind I am on a tablet, so please bear with me on this one. It's as good as I can get here. Oh, it's horrible to try and draw on a tablet. So let me just bring this down here. So there we go. Oh, no. Being mean. So I've got here, I've got zero velocity, so zero gradient. This one here, positive, or no, sorry, positive, negative, so maximum negative gradient, so I've got negative velocity. At this position here, 0, so at 25, I've got 0 again. This position here, I've got a nice positive gradient. It's the biggest positive gradient I'll get, so I get a nice velocity that's positive. 0 at 50 there, and back down to a negative gradient there. That was really difficult to try and draw. I do apologise. So this kind of question, they like doing these kind of questions where they make you graph backwards and forwards. It's really important that you can either have a reference point, or I tend to work, when I'm doing graphs, I tend to work on the zeros where I get crossing points or I get gradients of 0. And that's what I tend to work with, those points. I don't work with points in between. So this is only worth 1 mark. And it's only worth 1 mark for this. So you could 1 mark for this. You could have actually used the fact that you know that x equals a cos omega t, and that is on your data sheet, so you could have used that there. Or you can just memorize how these graphs work. State at one time at which the plate has maximum potential energy. So this is when they have maximum potential energy. Okay, so at any time on here, so if we go to the answers, there's lots of times you could have picked here. So any of the following velocities is 0. So I'm just going to literally copy and paste this. Oops. Copy and paste, I'm going to put this as my answer. Basically, potential energy is, of course, when the maximum potential is when kinetic energy equals 0. Because in any SHM system, it is going between a potential energy and a kinetic energy. So to have maximum potential energy, you must have 0 kinetic energy. So I'm looking for positions, if I actually go back here, where I'm going to have 0 velocity. So it's 0, 25 milliseconds, 50, and 75. And if I just copy and paste the mark scheme in, you'll see that literally they're accepting any of those answers there. So there we go. As you can see, they are allowing any of those answers there. So this is when maximum potential energy, it's all about this idea that that's when you're going to have no kinetic, all potential. So it could be a spring or an system there. So they're allowing any of them. So let's go on to the next question. So that was just some using your graph. This one here is quite interesting. So a small quantity of sand is then placed on the surface of the plate. So the plate's the thing that's being forced to oscillate. Initially, the sand grains will stay in contact with the plate as it vibrates. So it means that as the plate vibrates here, the sand will stay in contact with it. The amplitude of vibration remains constant at about 3.5 times 10 to the minus 5. So what it's doing is it's staying at the same amplitude, so it's still moving. But above a certain frequency, the grain of sands lose contact with the surface. So what happens is when it oscillates, so in particular when it falls down, what actually happens is the plate falls down quicker than the actual sand would fall. And this is all to do with the fact that the sand is not attached to the plate. So when the sand moves down, it's actually moving down with G. So explain why and how and why this happens. So it's a 3-mark question, and it says here that for me it'd be the sand stays in contact when the object moves down with an acceleration that is less than g. So what will happen is that when this object's moving down, if it's moving down, so if I let this free fall, that's how the sound would move. It will accelerate downwards at g. But if it's attached to this, as you can see here, they're both moving down at g, they both stay attached to each other. But if this plate was moving faster than g, it was accelerating downwards faster than g, this thing here will still move at g. So the sand stays in contact when the object moves downward less than g. Since acceleration equals omega squared a, and omega is 2 pi f, if the frequency increases, then a would too. If the acceleration becomes greater than g, the plate will accelerate faster than the sand falls, therefore it loses contact. So what's actually happening here, like I said here, is if they were both moving downwards at g, they stay contact with each other. But if this plate was moving faster downwards than this, it would actually lose contact because there's nothing sticking them together. They are two separate entities. Okay. So if I go to the Mark scheme in this one, Mark scheme says when the vibrating surface accelerates down with an acceleration less than the acceleration of free fall, the sand stays in contact. So it's exactly what I said at the start. The sand stays in contact when the object moves down with an acceleration less than g. Okay. Above a particular frequency, the acceleration is greater than g, or there is no contact force with the sand. The sand is no longer in contact when the downward acceleration plate is greater than sand due to gravity. So I actually gave a little bit too much information there. And actually, because I said since A is omega squared A and omega is 2 pi f, if f is a greater, A would 2 be greater. And that actually, I was saying about the frequency and the acceleration, I've actually gone into the maths of it. So I've got even more detail than I needed. But that's the kind of thing I would do. When I'm trying to say that if something goes up and then something else goes up, I like proving it with the formula. So I like saying if acceleration goes up because frequency goes up, I want to kind of back it up with the formula. It's a really good habit to get into. And lastly, of course, if A is greater than G, the plate will accelerate faster than sand, so it loses contact. Last mark. So it says here, calculate the lowest frequency at which the sands lose contact with the surface of the plate. So I know that at G is the last position. If the acceleration of the object oscillating is bigger than G, I know that that means it's going to lose contact. So G is the lowest, sort of the lowest that you can actually have. So I've got A is going to be G, and that's going to be omega squared A. I know my amplitude is 3.5 times 10 to the minus 4 meters. So I've got G equals omega squared times by 3.5 times 10 to the minus 4. Omega is going to equal 9.81 divided by 3.5. Oh dear. 9.81 divided by 3.5 times 10 to the minus 4. So that's going to be 28,028. Square root that, and I get omega is 167 rads per second. And of course, I know that omega is 2 pi f. So 2 pi divided by that, right? My answer divided by 2 divided by pi. Why have I just done the modulus here? And I get an answer of a frequency of 26.6 hertz. Go check the mark scheme. And I get an answer of 26.6 hertz. So nice. So I get a mark here for actually working out the formula or setting it as G, and a mark for the answer for the frequency. So when I was actually doing the formula, that really helped me with this question here, that I was able to identify what was going on. So that was just the written question. That's a written question from the specimen paper and how to do it. What I'm going to do now is I'm going to do the multiple choice. So there are 3 multiple choice that we're going to look at. I'm going to explain how you answer them. So the joy of multiple choice with SHM is it normally comes with graphs or comes with like things, definitions, etc. So this one here is the graph that shows velocity moving with simple homology varies with its displacement. So also know how its velocity changes with its displacement. So this one here means that no matter where I am displaced, the velocity is constant. So that's completely and utterly incorrect. This one has the displacement ever changing forever, and that one's incorrect. This one here, if you look at the displacement, so it has a positive and negative, as does this one. So it's down between these two. So let's actually think how the velocity changes. So if I move it back here, so I'm moving it negative, what happens is the velocity is going to go that way. So I've moved it this way, the velocity is going to go this way. But as you can see, when it gets down to no displacement, the velocity keeps moving in the same direction until I get to this point where it stops. So when I'm at maximum displacement, I have no velocity. But when I have zero displacement, I do have maximum velocity, which you should know from your energy changes. So it goes potential to kinetic. So the only one that shows when I have zero displacement, maximum velocity, is this one here. And that one is correct. Okay. This one here, if you look at it, actually just shows that you have zero velocity when you have zero displacement. So it's saying that when I'm in the center, I have no velocity, which makes no sense. Okay, the frequency of a moving body in a simple harmonic motion is doubled. The amplitude remains the same. What is also doubled? Okay, so when I see the word frequency and I see SHM or circular motion, I immediately write this down. Okay, I just immediately write that down, or 2 pi over t, just so I'm aware that's the form you're going to do. So which of these is also doubled? So first of all, the time period. So what I'm going to do is we're going to write down the relationship between frequency and the time period, which is frequency is 1 over t. So if I double that, that ain't going to be doubling. So it's definitely not that one. The total energy of the system. So energy is a half of v squared. Or of course MGH. Do apologise, it's hay fever season here at the moment. So the total energy here. So let's actually look at this. So I've got a kinetic energy, and that's a half v squared. So the maximum the kinetic energy could be is of course a half v max squared. And I know that v max equals omega A, and the amplitude is not changing. And so V max equals 2 pi F A. So my velocity, if my frequency doubled, my velocity would double. But if you look at the kinetic energy, it's going to double and then it's going to double again. So it's actually going to quadruple the amount of energy in the system because it's V squared. So it's not this one. Again, the maximum velocity, if you look at this one, that is going to double. So back to what I was saying here, if F doubles, that doubles. So that's correct. And go to acceleration. So A max equals omega squared A. So that's going to be 2 pi F squared A. And as you can see here, one of the things we've got a problem with there is that it's F squared. So that's actually going to be, not only are we going to double that, that double is then going to be squared. So the acceleration is going to quadruple. So the answer to this one is C. So like I said, one of the things I like doing is when I see these kind of things about what's also doubling, I like writing formulae down and actually going, cool, well, we're going to do this. But if you do see frequency in SHM, the first thing I normally write is this omega formula out, or 2 pi over t, and I start trying to relate it all around. By the way, the examiner, when you actually colour these in, you're supposed to colour them in here. Okay, I'm just circling that to make it obvious. Make sure you do circle it. Don't miss any multiple choice out. But the examiner will not take consideration of any of your working around it. They're only solely looking at these dots that you put in. So, question 4. A particle oscillates with undamped SHM. The acceleration of the particle is always in the opposite direction to the velocity. No, that doesn't make sense because it's either, if you think about it, the acceleration changes direction constantly. So in this position, the acceleration is going this way. When it's going this way, the acceleration is slowing down. So the acceleration up to here is speeding it up. So it's in the same direction. And then after here, it's slowing it down. So it changes direction. So that one's incorrect. It decreases as potential energy increases. That's also incorrect because where you have most of the potential energy is, of course, when you're mostly displaced. And since A is proportional to minus X, most displacement is most potential energy. So therefore, A is also going to that. So that's also incorrect. Proportional to its frequency, that kind of brings us back up to this one here, that A equals omega squared A, which means it's not proportional to the frequency. It's actually proportional to the frequency squared. So it leaves us the last question. So it is least when the speed is the greatest. And that makes sense. When you've got the maximum speed, your acceleration is actually 0. So the answer to this one is this one here for 1 mark. So these are just multiple choice questions. And again, you can draw all over it here. But it's really important that the examiner will not take consideration. You can doodle, write and stuff. They're only going to take consideration to actually what you filled in here. And remember to fill in with the circle. I circled it to make it obvious to you, but how you fill it in is you colour in that dot. If you go to the front screen of the multiple choice, to tell you if you change your mind, what you need to do. So please be aware of that kind of thing. So there we go. That is SHM questions from the Specimen paper. Hopefully they'll help you, and I'll do a few more from other papers a bit later. Okay, guys, take care.